Hello everyone, welcome to the next part of this module where we discuss about the key features and the differences between microprocessor and microcontroller, where we talk about the key features, the history and the future scopes of this. So welcome to the video, myself Anubhab Sarkar, Assistant Professor EEE Department SVIST. Let's get started. So, in first, we have to know this how to simple break down the key differences between microprocessor and microcontroller. In the definition part, in microprocessor, it is a central processing unit. We all know it's a CPU, and in microcontroller, a full computer system on a chip that is CPU plus peripherals all integrated. In components, only the CPU needs external RAM, ROM, and input output in microprocessor. And in microcontroller, it includes CPU, RAM, ROM, input output ports, timer, etc. on a single chip. What are the usage of microprocessor? General purpose computing, PCs or laptops. Whereas in microcontroller, specific control tasks, that is appliances, embedded systems like this. And what are the examples? Intel Core, we all know AMD Ryzen, and in microcontroller it's Atmega, STM32 ESP, all this like this, etc. Microprocessors are brain that need a body, and in microcontrollers are brain with a body, all in one chip. So that's in short. So then going to the next slide. Here we have to know how the history overview. The evolution of microprocessors and microcontrollers is like the story of modern computing itself. Let's go on a quick tour through time, hitting the major milestones and breakthroughs that shaped both technologies. First is the birth. Microprocessor in 1970 and in microcontroller it is 1974, where Texas Instruments developed the TMS 1000, the first microcontroller. It had ROM, RAM and the input-output in one chip. And in microprocessor, which was established in 1970, Intel introduced the Intel 4004, the first commercial microprocessor. It's a 4-bit chip designed for calculators. Next point is the growth and expansion between 1980s to 1990s. In microprocessor, Intel launched the 32-bit family, eventually powering IBM PCs. And in microcontroller, it became standard in appliances like toys, vehicles. Companies like Atmel, PIC and Motorola made affordable 8-bit MCUs, like embedded system emerged. Next part is the revolution and ubiquity. In microprocessor, multi-core CPUs become the normal. Multiprocessors gain popularity. And in microcontroller, Arduino, Atmega, ESP, Node MCU all are the normal. Next one is the future trends. In future trends, Edge AI running machine learning directly on microcontrollers, neuromorphic computing, that is chip modeled after the human brain, and quantum and photonic processors are also being explored, through still experimental. Clear? Going to the next slide, where we discuss about the architecture of both this microprocessor and microcontroller. First, system on chip versus CPU only. That is, in microcontroller, the architecture is simple. System on chip includes CPU, RAM, ROM, flash, timers, input output, ADC, that is analog to digital converters, etc. Whereas in microprocessor, it's CPU only. RAM, ROM, input output, etc. Must be added externally, that is Intel i7, i9, i9 or AMD Ryzen. In memory acquisition, RAM-ROM in microcontroller one chip small size 2 KB to 512 KB, but in microprocessor its external is large like 500 GB, 200 GB, 1 TB like its RAM, and its speed first access closer to CPU in microcontroller. Microprocessor slower due to external connection. In memory control managed by the chip itself in microcontroller, but in microprocessor in speed memory needs external memory controller. Its power and clock comparison in microcontroller in power very low, suitable for battery powered systems, but in microprocessor it is high power, requires cooling and constant power higher. Clear? And in application focus, microcontrollers, small task specific system like sensor, motor control, wearable technologies. But in microprocessor, heavy duty computation, that is OS, multitasking, graphics, data crunching. So in short, both microprocessor and microcontrollers are absolutely vital across industries, but they are used differently depending on the task. Here's the breakdown of how they are applied in healthcare, automatic and smart home environment. Next slide. So these are the applications. First is healthcare, second one is automotive, and third one is smart home. There are a lot more examples are there, but in healthcare, we all know in microcontroller, wearable health monitors, that is heart rate, glucose, fitness trackers like Fitbit. We all know nowadays. Second one is portable diagnostic tools like digital thermometers, oximeters. Third one is medical infusion pumps. Fourth one is smart prosthetics. In microprocessor, what are the healthcare applications? Advanced imaging systems like CT, MRI, and ultrasound machines. Second one is patient monitoring system, that is multi-sensor data processing and display. Third one is hospital management system, we all know. Fourth one is AI-based diagnostic tools, running deep learning models for image recognition or data analysis. Next part is the automotive. Automotive means a vehicle. So in microcontroller, what are the examples? Engine control units, that is ECUs, managing fuel, injection, timing, etc. Second one is airbag system, there is superfast sensor data processing for deployment. Third one is parking sensors. Fourth one is power window, seat, mirror control. The last one is tire pressuring monitoring system. All depends on microcontroller. In microprocessor, what are the automatic applications now? In microprocessor, infotainment system, that is touch screen, navigation, voice control, all depends on microprocessor. Second one is advanced driver assistant system, processing camera, radar and LiDAR data. Next is digital instrumental cluster, autonomous driving computers, all under microprocessor. Now the last but not least, smart home. In microcontroller, smart thermostats, that is which control heating cooling intelligently. Second one is light automation. Third one is smart locks and security system. We all know about this in the smart gadgets, IoT applications. All depends on microcontroller and smart home. But in microprocessor, why do we get to know smart homes? Smart home hubs, that is Alexa, Google Home, etc., which needs to process voice, run apps, and connect multiple devices. Second one is home server, media center, AI based assistance, all under the smart home. Clear? So these are the applications we all know in the modern era. Going to the next slide, this is the performance matrix. So in performance matrix, first is speed analysis. In speed analysis, we have to know the clock speed feature for both of these. In microcontroller, clock speed features typically from 1 to 100 megahertz, and in microprocessor, it is typically 1 to 5 gigahertz. In multitasking, in microcontroller, limited or single threaded, and in microprocessor, it is full multitasking with OS support. Performance per task. Next point feature. In microcontroller, it is high for simple task, low latency, and in microprocessor, high for complex multitasking job. Use an MCU if you are doing simple, repetitive, low power control task, but use an MPU, that is microprocessor, if you are building system that need multitasking, large memory, or rich interface. Next one is the efficiency. Efficiency is in microprocessor, efficiency is more than the microcontroller, but in small task, in microcontroller wins the race. That is, in microcontroller, it is dedicated to small task, where the efficiency is more than microprocessor. But overall, both of them are dedicated to some different work. Third one is the power consumption. Power consumption in microprocessor, it's high. We all know that is computer, laptops. It's high consume power, but in microcontroller, it is low for power consumption. Clear? Now moving to the next slide, the development tools. How the tools are developed. There is programming, debugging, testing, and efficiency. So how it happens? Let's get started. First one is the IDEs, Integrated Development Environment. like Arduino IDE, STM32, MPLAB IDE, Platform IO. These are the programming platforms. That is the IDE, Arduino IDE, Integrated Development Environment. In programming, the next point is compilers. Compilers, we all know, without the compiler, it is impossible to perform a task. The tools are GCC for ARM, AVR, GCC, XC8, and IAR Embedded Workbench High Performance Commercial Computer Suite. Third one is programmers and debuggers. The tools are ST-Link, AVR ISP, J-Link, and Picket. Fourth one is simulation, the most important part. Simulation needs Proteus, that is a circuit simulation with MCU code execution. Second one is QEMU, that is lightweight emulator that can emulate some MCU families. Third one is a Cigar Ozone. But in microprocessor development tool, what are the tools? Microprocessor IDEs, that is a code editor. There is Visual Studio Code, Eclipse, Q2 Creator, Celeon. Second one is the operating system and SDKs. Operating system we all know. What are the tools? Buildroot, Linux, Android. And in debugging, the tools are GDB, Valgrind, Strace, and Perf. And in emulators, that is the virtual machines, we all know the tools are QEMU, VirtualBox, and VMware. So these are the programming, debugging, testing, and efficiency. So after this clear, these are the development tools. So moving to the next slide. The market trends. In MCU market size, it is expected to reach $48 billion by 2027, driven by IoT, which is very recent nowadays, which needs automotive and wearables. But in MCU market size expected to grow 120 plus billion with demand in smartphones, cloud AI, and autonomous systems. Clear? In today's ever-evolving landscapes, it is crucial to analyze the current market share, but we can predict the future projection of microprocessor and microcontroller, which is increasing day by day. By understanding market trends, we can still stay ahead of the curve and drive in innovations. Thank you.